In a previous video, I posed the question, how can we measure the specific heat of an object? In particular, I gave the scenario that I hand you a lump of metal in my kitchen, which has lots of good things like, pots and pans and a kitchen scale and an instant read thermometer and cups and mugs and all sorts of things. And I said, how would you use my kitchen to find the specific heat of the material that this lump of metal is made of? And after making people pause and think about their own method, I gave mine. May or not be, people may have come up with other ones, but this was the method I came up with, which was to measure the mass of my lump of metal with a scale. There's the answer I got. To boil some water and get the metal in equilibrium with it, so I had this initial temperature for the metal. I put a known mass of water into an insulated mug, and I checked its temperature, and this is the temperature I found. And then I put the metal. I used pulled with tongs, pulled the metal out of the boiling water, put it immediately into the mug, and I waited for the metal and water to come to equilibrium while the insulation kept it safe from outside, and I got this final temperature. That was the method I came up with. In the previous video, I went through a sort of intuitive way of going step by step to figure out what the specific heat of the metal was by calculating heats and heat capacities and things one step at a time. I want to sort of put this together in a slightly more formal, symbolic way, just to show another way of doing this problem, maybe my favorite way of doing this class of problems. And we'll do that in a second. So the plan is, we've got all this data, and we know some things. We know that specific heat is heat capacity per gram. We're doing per gram, not per mole. We're doing that definition of specific heat. And heat capacity of an object is, well, the original definition is heat divided by change in temperature. You put in a certain amount of heat, you see how much the temperature changes. That's the heat capacity of that lump of stuff. But we can use the first law of thermodynamics, which is just conservation of energy, to say, hey, if the change of energy of my substance is equal to the work done on the substance plus the heat put into the substance, then I can rewrite this Q as delta U minus W. Different people use different conventions for whether work is positive or negative in these, but it doesn't matter, because for us, we'll find there isn't any work being done while the metal just sits there in the mug. We know that work equals 0 in that case. There's no work being done. Maybe there's some tiny thermal expansion and thermal contraction. I'm not going to worry about it. I don't think that's going to be a significant factor for, compared to the other things. So work is basically 0. That means that our C is delta U over delta T. And I can go through then and say that the heat capacity, for example, of the water is going to be, well, if I solve the heat capacity of the water is, oh, wait, that's not even what I want. I want to do this the other way. If I'm doing it this way, I want to say, let me write the delta U of the water, the change in thermal energy of the water. Delta U of the water, if work is 0, I can solve. It is the heat capacity of the water. That's a C, really it is. C times delta T of the water. And then heat capacity is mass times specific heat. So this is mass of the water times the specific heat of water times, and for delta T, that is T final, that's the same for both substances, minus T initial for the water. That is my delta U for the water. And I can write down precisely the same reasoning for the metal. I know that delta U of the metal is going to be, same reasoning, it's going to be the mass of the metal times the specific heat of the metal times T final, that's the same for both because it's equilibrium, minus T initial of the metal. That's my delta U of the metal. So that's just using these definitions and the fact that there's no work in the story to come up with expressions for delta U. Why did I do that? Well, it's because when I put them together, I know that for my whole mug, plus the whole mug full of stuff, for the whole mug together, I know that the mug is insulated from the outside, so delta U of the total system is going to be work plus heat, but work is 0 for the same reason we said earlier. It's just sitting there. There's not any significant expansion or contraction. And heat with the outside, it's insulated, so that means heat is also 0. So delta U total is 0. At that point, since the change in total energy is 0, at that point I can go back and look at these. there are only two things inside the mug. I'm ignoring the fact that part of the mug is also going to come up to temperature because that's a complicated thing. We're going to assume that that's not a significant factor along this. That's a bit of a fib, but I'm not quite sure how to deal with it otherwise, especially in my kitchen. So that's going to be a fudge factor, so it's not quite right. So we go through. Delta U total is work plus heat, which is 0. So that means that 0 equals delta U water plus delta U metal, the sum of these two things. So that means mass of the water times C water times T final minus T initial water plus mass of the metal, C metal, times T final minus T initial metal. And this equation, where we have 0 equals the sum of these terms, this is useful in all sorts of places because I can use this and solve for whichever thing is my unknown. If I had known both specific heats and I wanted to know the final temperature, I could solve for T final. If I wanted to find what the initial temperature of the metal was and I knew its specific heat, I could solve for that. But in this case, I want to solve for C metal. And so I can just do that. Let me do that in my next line right here. Solving for C metal, I guess I'd better subtract this term from both sides. So I will get mass of the metal, C metal, T final minus T metal equals negative mass of the water, C water, T final minus T initial metal, T initial water. I got that. And then to solve for C metal, I just divide. I'm going to divide by that. I'll find that C metal equals, okay, this thing, minus mass water, C water, T final minus T initial water, divided by mass of the metal times, not a final, T final minus T initial metal. There we go. That's going to come out to what we need. And now we can just plug in all those pieces. My mass of the water was negative. I've got the negative sign, the minus 250 grams times specific heat of water is 4.2 joules per gram degrees Celsius times my change in temperature of the water, T final minus T initial for the water is 4 degrees Celsius. That's not a good. 4 degrees Celsius. 4 degrees Celsius divided by the mass of the metal was 100 grams times the change in temperature, final minus initial for the metal. Final minus initial that's my negative 76 degrees Celsius. And you can see from all this that the grams will cancel with grams, the degrees Celsius will cancel with degrees Celsius, and you're left with just specific heat units. When you plug through this, when you plug this in, you'll find the same answer I got before, that this is 0.525 joules per gram degrees Celsius, which is a plausible specific heat for a metal. It's much less than water, but not enormously less. So yeah, that's the method, a different method for solving the same problem, and I hope it makes sense. This one is based on setting up an equation for general problems like this, that you could use this equation to solve almost anything. And of course, this important equation I'm talking about that's so useful, I've crammed in a two-line thing here. Sorry for being a little less than clear with it. But this form, where you do mass times specific heat times change in temperature and just add it up for all the components of the system, and set it equal to 0 if you're insulated, that form is really useful because you can use this form for solving for anything that's an unknown in this story. T final is probably the trickiest thing to solve for just because it appears in both terms. You have to expand it all out and solve for T final. But again, that's just algebra. And hopefully you're good at algebra. And if you're not, hopefully your teacher gives you partial credit if you screw it up. So that's the deal. It's the same result as we got in the previous method. It's just this slightly more general equation we came up with for approaching this type of problem is kind of nice to have. It's kind of nice to have this symbolic equation to relate all the quantities of importance. You can use it for lots of things. And with that, that's all I wanted to say about this example. Measuring specific heat, a method, and some math. There you go.